Are you a software engineer preparing for system design interviews and looking to confidently ace them and reach the next stage in your career? Or maybe you're a software engineer who wants to level up. Think like a senior engineer and start designing scalable systems and architectures with confidence. If so, this course is designed for you. What makes this course different is that it doesn't just focus on the technical side of system design interviews, it also teaches you how to structure your answers and communicate your ideas effectively. Communication skills are just as important as technical skills, and interviewers evaluate both. In this course, you'll learn not only the technical and non-technical foundations of system design, but also the latest technologies used in modern distributed systems and how to choose the right technologies for different scenarios. The course is continuously updated to reflect the latest industry trends and technologies. You'll start by building a strong foundation in system design, learning the essential concepts every successful system architect should understand. Then, you'll dive into data storage in distributed systems, including different types of databases, object storage solutions, and strategies for storing and querying data efficiently. After that, you'll explore the core components and architectural patterns that power modern distributed systems. You'll also learn about the most important technologies widely used in real-world scalable systems today. Next, you'll learn a complete framework for approaching system design interviews, including how to structure your answers clearly and communicate effectively throughout the interview. And to help you apply everything practically, the course includes quizzes and complete mock system design interviews. By the end of this course, you'll have the knowledge and confidence needed to succeed in system design interviews, think like a senior engineer, and start designing scalable systems with confidence.
Let's begin by understanding what is meant by system design. The definition of system design is the process of planning how different parts of a software system work together. Imagine this: you built a simple website, maybe a URL shortener like Bitly. At first, it worked perfectly for 10 users. But then suddenly 10,000 users show up, then 1 million, suddenly your website crashes. That's because your system wasn't designed to scale. That's why system design is important. As developers, we don't just write code, we build systems that people depend on. When we design systems, we must consider designing a reliable system that can scale easily, handle large-scale data, and can recover easily from disasters. The main building blocks of any system are the client. This could be a web, desktop, or mobile application, for example. The server, this is where the application code runs. The database, this is where the data of the application is stored. And network, this defines how all these components communicate with each other. Your task as a system designer is to connect all these components efficiently. You should approach any system design interview by following these 5 steps. Clarify requirements, define scale, propose a high-level design, then deep dive into some of the components, and finally discuss the trade-offs. Let's talk about each step in more detail. First, clarifying the requirements. There are 2 categories of the requirements: functional and non-functional requirements. Functional requirements are what the system does, for example, for a chat application. Sending messages and sending notifications are functional requirements, while non-functional requirements define how the system should behave. For example, performance, scalability, and latency. The next step is defining the scale of the system. Ask the interviewers questions like how many daily active users, how many requests per second, and how much is the data size. This will affect the decisions you will make later when you design the system. Then propose a high-level design. Keep it simple, don't deep dive into any components yet. Just make sure that this design meets the functional requirements. Then deep dive into some of the components. If the interviewer didn't explicitly ask you to deep dive into a certain area, choose any component or topic where you have more experience and deep dive into it. For example, the database choice, caching strategy, or sharding strategy. Finally, discuss trade-offs. This is a very important seniority signal for the interviewer. Explain why did you make certain choices and what are the alternatives, and what are the pros and cons of each choice. Scalability is the ability of a system to handle more work or growth without breaking or slowing down too much. In plain English, If your app suddenly gets more users, data, or requests, can it still perform well? Scalability is very important in designing systems. It ensures resilience and adaptability. Without it, systems suffer downtime, high latency, or reduced performance during high activity. There are mainly two types of scaling a system: horizontal and vertical scaling. Vertical scaling means making a single machine more powerful. For example, upgrading the CPU, the RAM, or the storage. Horizontal scaling means adding more machines instead of upgrading one. We are going to learn more about both approaches and how to choose between them later in the course. Reliability in system design refers to the ability of a system to consistently perform its intended function correctly and without failure over a specified period of time, even under varying conditions. Reliability is important in system design since it ensures continuous operation. Reliable systems avoid unexpected failures. This is critical for services like banking and healthcare, where downtime can disrupt millions of users. It also improves user trust and experience, reduces the cost of failures, and supports scalability. A system that is not reliable will struggle as it grows, so reliability ensures that performance remains stable even when demand increases. Reliable systems are often designed with redundancy, backups, and failover mechanisms, so they can continue operating even when parts fail. Availability in system design refers to the ability of a system to be operational and accessible when users need it. It is usually expressed as a percentage of uptime over a period of time. For example, a system with 99.9% availability, also known as 3 nines, is down for only a small amount of time each year. And don't underestimate the decimal numbers. 99% availability means the system is down 3.75 hours per year, which is not acceptable for most of the systems. Some of the techniques to achieve availability are replication, load balancing, failover, and health checks. So we will learn about these techniques in details later in the course. Fault tolerance is the ability of a system to continue operating correctly even when one or more of its components fail. Fault tolerance is important in system design since it prevents complete system failure. Instead of crashing entirely, a fault-tolerant system isolates the problem and keeps the rest running, which ensures the system availability and improves the user experience. Fault tolerance also reduces data loss, since fault-tolerant systems often include replication and backups, ensuring data is preserved even if hardware or software components fail. Imagine this: you tap a button on your phone to order food. You expect it to respond instantly, okay? Maybe show a loading spinner, confirm your order, or update your cart. But instead, nothing happens for 5 seconds. What do? You tap again. Maybe you refresh. Or worse, you close the app. That delay, that's latency. Latency is the time it takes for a request to travel from the user to the system and back with a response. There are 3 types of latency. Network latency, which is the time taken for data to travel over the internet. Processing latency, which is the time the server takes to compute the result. Disk latency, which is the time required to read or write data from storage. Latency directly affects user experience, system performance, business success. Even a 100 millisecond delay can noticeably reduce engagement. So in system design, reducing latency is one of the most important goals, and you will learn different techniques later in the course to achieve that. Let's go back to the example from the last lecture. You tap a button on your phone to order food. You expect it to respond instantly, maybe show a loading spinner, confirm your order, or update your cart. But instead, nothing happens. Not for 5 seconds, nothing happens at all. The app freezes. That's because thousands of people are ordering at the same time. The system might not be failing because it can do the work, but because it can't do enough work at the same time. That idea is exactly what we call throughput. In system design, throughput tells us how many requests a system can handle, how fast it can process data, whether it scales under real-world load, and it is one of the most important performance metrics. Let's talk about some of the most common systems architecture patterns. First, the monolith architecture. A monolith is a single unified application where everything is bundled together, while microservices architecture breaks the system into smaller independent services. Imagine a food delivery app. In a monolith architecture, all the app modules are in the same code base. While in a microservice architecture, the app is separated into services. Each service has its own code base, and they communicate with each other through APIs. The advantage of microservices is ease of scaling and deployment. Also, if any issue happened with one of the services, the other services are not affected. Client-server architecture is a distributed application model where multiple clients request services or data from a centralized server, which processes these requests and manages resources. The client is a website or a mobile or desktop application, while the server is a computer that stores the system data, processes client requests, and sends responses back. The communication happens between the client and server via APIs. A three-tier architecture is a software design pattern that organizes an application into three logical and physical computing layers: presentation, application, and data. The presentation layer is what the users see, for example, the mobile app or website UI. The application layer contains the business logic and processes the requests from the presentation layer. The data layer is where the system data is stored and retrieved. It's typically a database and the code that stores and retrieves data from it. Let's understand the foundational communication protocol HTTP and the difference between HTTP and HTTPS. HTTP, which is an abbreviation for Hypertext Transfer Protocol, is the basic protocol used for communication between a client and a server. It defines how requests and responses are structured. The issue with HTTP is that it's not secure. Data is sent as plain text. And that's what HTTPS solves. HTTPS is an abbreviation for Hypertext Transfer Protocol. So it's basically HTTP plus encryption. The encryption protocol is SSL/TLS. Data is encrypted, and that prevents attackers from reading or modifying data. TCP, which is an abbreviation for Transmission Control Protocol, is a communication method that ensures data arrives correctly and in order, and missing data is sent again. First, a connection is established. This is also known as a handshake. Then data is sent in chunks. Then the receiver confirms each chunk. Then missing chunks are sent again. It's a reliable protocol, but it's slow for things like streaming and online gaming, where speed is more important than accuracy. And that's what UDP solves. UDP, which is an abbreviation for User Datagram Protocol, is a faster but less reliable way to send data. It doesn't guarantee the delivery or the order of the data, and there is no error checking. It's fast but not reliable, and mostly used in streaming, voice and video calls, and online gaming. Let's talk about DNS resolution, which is something that powers almost everything you do on the internet, but is often invisible. Every time you type a URL into your browser, your system needs to figure out what is the IP address of this domain. That process is called DNS resolution. Let's start with a simple question. Why don't we just use IP addresses instead of domain names? Because domain names are easier to remember than numbers. Also, IP addresses can change, while domain names don't. DNS stands for Domain Name System, and it's a distributed database that maps domain names to their IP addresses. Let's walk through what happens when you type a URL into your browser. First, the browser checks the local cache. If the mapping is not found, the operating system checks the DNS cache. If there's no caching, then the request goes to the DNS resolver, and the DNS resolver returns back the IP address to the browser. Then the website loads. The CAP theorem states that in a distributed system, you can only guarantee 2 out of these 3 properties at the same time: consistency, availability, and partition tolerance. Hence the name CAP theorem, the first letter from each of these words. We already learned about what each of them means, but let's see their definitions again. Consistency means every read receives the most recent write or an error. In simple terms, all users see the same data at the same time. Availability means every request receives a response, without guarantee that it's the latest data. In simple terms, the system always responds, even if the data is slightly outdated. Partition tolerance means the system keeps working even if parts of it can't communicate. In real-world network failures will happen, no way around it. So partition tolerance is non-negotiable. You must choose between consistency and availability. It's not possible for a system to have both consistency and availability at the same time with partition tolerance, because during a network partition, the requirements of consistency and availability directly conflict. Imagine the data of a system is partitioned into 2 servers. Then a network partition happened. Now the servers can't communicate. Then a user updated a value, let's say X, from 50 to 100 in server A. Now another user is reading this value from server B. If the system is consistent, that means server B must return the most recent value, which is 100. And if the system is available, that means it returns any value regardless if it's the most recent or not. Since there is a network partition, server B can either return 50, which makes the system available but not consistent, or return an error, which makes the system consistent but not available. Each time you design a system, you have to think about the trade-offs between consistency and availability and choose accordingly. Imagine you're using a banking app. You transfer $100 from your saving account to your checking account. Immediately after, you check your balance. On your phone, it shows updated balance, while on your laptop, it still shows the old balance. Now you're not sure if the transaction actually happened. This is exactly the kind of problem consistency in distributed systems tries to solve. In large-scale systems, data is stored across multiple machines. Keeping all copies perfectly in sync is not as simple as it sounds. When designing systems, you constantly face trade-offs. Should users always see the latest data? Or is it okay if data is slightly outdated for better performance? Understanding consistency in the CAP theorem helps you make these decisions intelligently. Consistency means every read receives the most recent write or an error. In simpler terms, all users see the same data at the same time. There are 3 types of consistency. Strong consistency, which means every read gets the latest value and there's no stale data ever. Some examples are banking and payment systems. The downside of strong consistency is that it's slow and has higher latency. Then eventual consistency, which means data may be temporarily inconsistent, but eventually everything syncs. Some examples are social media and DNS resolvers. The downside is that users will see stale data briefly. Then weak consistency, which doesn't guarantee when updates will propagate. This is rarely used in critical systems. Let's understand what is meant by availability in distributed systems. Availability means every request gets a response, even if the response is not perfectly up to date. The system never says, "I can't respond." It may return stale or cache data, but it always replies. Systems achieve availability by replication, which means storing multiple copies of the same data in multiple databases. If one fails, the other responds. The downside of this approach is when the data is updated, time is needed to update the data in all the instances, so sometimes users will read stale data. Caching also increases availability by retrieving data from memory instead of the database. Modern applications run on multiple servers across different locations, but networks are not perfect. Sometimes connections fail or regions go offline. If your system can't handle this, it crashes or behaves unpredictably. Partition tolerance means the system continues to operate even when there is a communication breakdown between parts of the system. A network partition occurs when some servers cannot communicate with others, so the system is split into isolated groups. Network partitions are unavoidable. So the real question is not will partitions happen, but how will your system behave when they do? SQL is an abbreviation for structured query language, and it's a language to communicate with relational databases. Let's first understand what relational databases are. Relational databases organize data into tables. Tables consist of rows. Each row represents a record. For example, in a user's table, a row represents one user, and columns represent attributes, for example, email and name. In relational databases, multiple tables in the same databases can have relationships, hence the name relational. For example, imagine a database consisting of users and post tables. Each post belongs to a user. So how do you know which post belongs to which user? By adding the user ID to each post, now there is a relation between the posts and users table. In this case, the user underscore ID field in the post table is called foreign key. And since it's a unique identifier for each row in the users table, it's called primary key for the users table. SQL is the right choice if the system has a lot of relationships. The disadvantage of SQL databases is the difficulty to scale horizontally and the rigid or non-flexible schema. Some popular SQL databases are MySQL and PostgreSQL. NoSQL is an abbreviation for not only SQL. There are databases that store and retrieve data in ways that are optimized for scalability, speed, and flexibility, not just structured tables. Unlike SQL databases, they don't have a fixed data schema and can easily scale horizontally. And unlike SQL databases, there are no relationships between tables. The drawback of this is a lot of duplicate data. For example, if there is a users table and post table, you can't join the post table to the users table by the user ID as in SQL databases. Instead, you have to add the entire user record to each post record, which results in duplicate data and difficulty to update the database. If you want to update a specific user, you must update it in all the records where this user is. NoSQL is a better choice than SQL if you need to scale or if the data structure is not fixed. There are different types of NoSQL databases: key value stores, document databases, wide column stores, and graph databases. We are going to learn about each type in more detail in the next lessons. A key value store is the simplest type of NoSQL database. Data is stored in key and value records. The key is a unique identifier and value is the associated data. Think of it like a dictionary or hash map in programming. This type of databases can easily scale horizontally. Partitioning of the data happens on multiple servers, and a hashing function determines in which server a record with a specific key exists. Common use cases of key value stores are caching, session management, and real-time analytics. Some popular key value stores are Redis, which is extremely fast in memory cache, AWS DynamoDB, and Memcache. If you've ever worked with JSON APIs, you're already halfway to understanding document databases. They store data in a very similar format. A document database is a type of NoSQL database that stores data as documents. typically in formats like JSON, BSON, or XML. Each document is a self-contained unit of data. Compared to SQL databases, each document is like a row in a SQL database table. For example, a document can represent a user in a database. And a group of documents is called a collection. In SQL world, this is like a table. Document databases have flexible schema. Each document can have different structure. Document databases are commonly used if the data schema is flexible and high horizontal scalability is required. The drawback of document databases is data duplication and the complexity of updating documents. Some popular document databases are MongoDB, CouchDB, and AWS DocumentDB. A columnar database stores data by columns instead of rows. For example, this is how a traditional row-based database stores data. And this is how the same data is stored in a columnar database. Each column is stored separately and contiguously. Columnar databases are optimized for analytical queries. For example, if you want to calculate the average of all the ages of the users, a row-based database would have to scan each row and extract the age value from each, while columnar databases will scan the age column only. Common use cases of columnar databases are analytics and business intelligence. The drawback of columnar databases are slow writes, because writing requires updating multiple column files. Some popular columnar databases are Apache Cassandra, Amazon Redshift, and Google BigQuery. A graph database is a type of NoSQL database designed to store and query relationships efficiently. Instead of tables or documents, it uses a graph structure where each node represents an entity, for example, a user, and each node represents a relationship. For example, user A is a friend of user B. Graph databases are perfect when there are a lot of relationships in the stored data. The drawbacks of graph databases are difficult to scale horizontally and high memory consumption. Some popular graph databases are Neo4j and Amazon Neptune. ACID stands for atomicity, consistency, isolation, and durability. It's a set of guarantees that ensure reliable and consistent database transactions. Before we understand what each of these means, let's first understand database transactions. A transaction is a sequence of operations treated as a single unit. This is what a transaction looks like. This entire block must behave as one indivisible operation. Now let's understand atomicity in ACID. Atomicity means that either the entire transaction succeeds or nothing happens. No partial updates are allowed. For example, in a bank transfer, a transaction contains two operations: debit $100 from account A, then credit $100 to account B. Without atomicity, the credit operation might fail, and account A would lose money. Atomicity guarantees that if an operation fails, the entire transaction is cancelled. Consistency ensures that the database always moves from one valid state to another. It means that you can't have invalid values stored in the database, such as a negative age or account balance. If a query results in an invalid state, it is cancelled. Isolation ensures that concurrent transactions behave as if they run one after another. Imagine two users withdrawing money at the same time. Without isolation, the total withdrawal may be incorrect. With isolation, each transaction runs in sequence, even if they start at the same time. In this case, the second withdrawal is rejected due to insufficient balance. Durability ensures that once a transaction is committed, it is permanently stored. Even if the system crashes or issues occur, the data remains safe when the system restarts. An index is a special data structure that helps the database find rows faster without scanning everything. Imagine a table of users, and you frequently query this table to search for users by their email. Each time the query has to scan the entire table, compare the email value of each record, with the value you are searching for until it's found or the entire table is scanned. This is not efficient and time consuming. Indexes solve this. Before we understand how, let's understand what an index is. An index is a special data structure that helps the database find rows faster without scanning everything. Usually an index is either a hash table or a tree-based index. In the previous example, if we create an index on the email, if it's a hash table index, then each key is the email and each value is the table row associated with it. If it's a tree-based index, in most databases, it's a data structure called B-tree, which is a balanced tree, and searching for an item has log n time complexity, which is much better than linear time complexity without an index. Let's see the different types of indexes. Primary index is an index automatically created on primary keys. Secondary index is an index created on any non-primary column. Composite index is an index on multiple columns. Hash index, which is a hash table based index, unlike tree based index, it's not efficient for range queries. The drawback of indexes is slow writing, even though indexes make reading faster, but each time a new record is written, the indexes are also updated. As systems grow, they inevitably face a fundamental challenge. How do we handle more users, more data, and more traffic? Scaling is the answer, but how you scale dramatically impacts performance, cost, and complexity. Let's begin by understanding what scaling is. Scaling is the process of increasing a system's capacity to handle load. There are two ways to scale systems: vertical and horizontal scaling. Vertical scaling means increasing the power of a single machine. For example, upgrading the CPU, the RAM, or the hard disk. The advantage of vertical scaling is that it's simple and easy to achieve. The disadvantage is the hardware limitation. There is no way to scale infinitely, and the system is still a single point of failure. Horizontal scaling means adding more machines to distribute load. Requests are distributed across servers using a load balancer. We will learn more about load balancers and how they decide which request goes to which server later in the course. The advantages of horizontal scaling is virtually unlimited scalability, fault tolerance, since if a machine goes down, another machine can handle the requests, and high availability. The disadvantages are the design complexity and data consistency challenges. Imagine you're building a system like a social media platform. Initially, everything works fine with a single database. At some point, vertical scaling is no longer enough or becomes too expensive. This is where sharding comes in. Sharding is a type of horizontal partitioning where you split your data across multiple databases called shards, so that each shard holds only a subset of the data. Determining how data is distributed across shards is done by the sharding key. For example, if RD is the shard key, then each shard stores users with specific IDs or range of IDs. That is defined by the sharding strategy, which we will learn about in the next lesson. In previous lectures, we explored why we need sharding, primarily to scale databases horizontally and handle large volumes of data and traffic. Now comes the question, how do we actually decide where each piece of data goes? That decision is defined by the sharding strategy. A sharding strategy is the rule or algorithm used to determine which database shard stores a particular piece of data. Typically, this is based on a shard key, a field in your dataset. For example, the possible shard keys for this dataset are user ID, country, and email. Let's go through the most important strategies used in real systems. First, range-based sharding. Data is divided into ranges of values. For example, shard 1 contains user IDs ranging from 1 to 1000, shard 2 from 1001 to 2000, and shard 3 from 2001 to 3000. That's a simple and intuitive strategy and efficient for range queries. The disadvantage is uneven distribution over time. Then, hash-based sharding. In this strategy, a hash function on the shard key. Unlike range-based sharding, the advantage of hash-based sharding is even data distribution, but the disadvantage is inefficient range queries. Imagine you're building a large-scale application, say a social media platform or an e-commerce system. Thousands or millions of users are reading and writing data every second. Now ask yourself, what happens if your database server crashes? Or if too many users try to read data at once? How do you ensure your system is always available? Replication is the answer for all these questions. Replication is the process of copying data from one server to one or more other servers so that all copies stay in sync. There are different replication types, which we will learn about next, but at high level, replication involves a primary node which handles writes, and secondary nodes, also known as replicas, which receive and apply updates from the primary node and often handle read requests. The advantages of replication are high availability, improved read performance. Instead of sending all queries to one server, multiple replicas handle read requests, data redundancy and durability, and geographic distribution. Replicas can be placed in different regions and users connect to the nearest server. In primary-secondary replication, the primary processes the write, then replicates the change to secondary nodes. Secondary nodes receive replicated data from the primary node, serve read requests, and act as backups if primary fails. Primary-secondary replication can happen asynchronous or synchronous. In asynchronous replication, the primary node does not wait for secondaries to acknowledge. This results in faster writes. But there is a data loss risk if primary crashes before replication. In synchronous replication, the primary node waits for secondaries to confirm. That results in strong consistency but slower writes. As we learned in distributed systems, data is often replicated across multiple nodes. That improves availability and performance, but introduces a key question. When I read data, will I always get the latest value? The answer depends on the consistency model your system follows. A consistency model defines the rules that determine what values a read operation is allowed to return. Let's start with the strong consistency model, which states that after a write completes, all future reads return the latest value. The downsides of this model is high latency, reduced availability, and hard to scale globally. Some use cases are banking systems and inventory systems. Then sequential consistency, in which all operations appear in a global order, but not necessarily real-time order. That means all nodes agree on the order, but timing may differ. Then causal consistency, which means if one operation causes another, all nodes see them in that order. For example, you'll never see the reply before the original post. Then eventual consistency, which means if no new updates occur, all replicas will eventually converge. For example, you update your profile picture. Some users see old pictures briefly, but eventually everyone sees the new one. Imagine you build a web application that suddenly becomes popular. At first, a single server handles all incoming requests just fine. But as traffic grows, response times slow down, and the server becomes overloaded. This is where load balancing comes in. Load balancing is the process of distributing incoming network traffic across multiple servers to ensure that there is no single overwhelmed server and that the system is highly available. The load balancer sits between clients and servers and decides where each request should go. When a request arrives, the load balancer receives it, then selects a backend server using a strategy, then forwards the request, then the server processes it and returns the response. Now the question is, how does the load balancer know to which server the request should go? There are multiple strategies for that, and that's what we will learn in the next lesson. In the previous lecture, we explored what load balancing is and why it matters. Now we'll go deeper into the core intelligence behind load balancers, the algorithms that decide where each request goes. A load balancing algorithm is a rule or strategy that determines how incoming requests are distributed across multiple servers. The goals of these algorithms are even distribution of traffic, minimizing response time, and maximizing resource utilization. Let's learn about the most common load balancing algorithms. First, round robin, which distributes requests sequentially across servers. It's simple and easy to implement, but can result in uneven workloads. Then weighted round robin. It works the same as round robin, but each server has a weight based on the capacity. Higher weight means more requests. This is more efficient than round robin, but still not dynamic, since it doesn't react to real-time workload. Then, least connections algorithm, which sends requests to the server with the fewest active connections. This algorithm adapts to real-time load, but the disadvantage is the overhead of tracking the active connections. Then, least response time, which chooses the server with the fastest response time. This optimizes user experience, but requires constant measurement of latency. Then, IP hash, in which the hash of client IP determines server assignment. That means the same user always goes to the same server, which is efficient for session management, but can result in uneven distribution. Let's understand the different types of load balancers. The layer 4 load balancer operates at the transport layer and routes traffic based on the IP address or the port number. It's very fast since it has the minimal processing time and it doesn't inspect the request content. The advantages of layer 4 load balancers are high performance, low latency, and simplicity. The disadvantages are the inability to know the request content. Layer 7 load balancer, which operates at the application level and routes based on the URL path, request headers, cookies, and the request content. The advantage of layer 7 load balancers are content-aware routing, the ability to perform authentication, caching, and SSL termination. The disadvantage is that it's slower than layer 4 load balancers. Imagine you're building a popular application, say a social media platform. Every time a user refreshes their feed, your system queries the database, processes logic, and returns results. Now multiply that by millions of users. Without optimization, your system becomes slow, expensive, and overloaded. This is where caching comes in. Caching is the process of storing frequently accessed data in a fast temporary storage layer so future requests can be served more quickly. The basic flow is the client requests data, the application checks if it's found in the cache, which is called cache hit, then it retrieves it and returns it back to the client. Otherwise, if it's not in the cache, which is called cache miss, the application fetches it from the database, stores it in the cache, and returns it to the client. The benefits of caching is faster response time. Since cache is an in-memory storage, it's much faster than databases. Reduced database load, since fewer queries go to the databases. Improved scalability, since the system can handle more users without scaling the database. And cost efficiency, since less compute and database usage is required. There are different types of caching, including client-side caching, which is stored in a browser or mobile app. CDN or Content Delivery Network, which caches static content geographically, and server-side caching, which is stored on server layer, and this is the most common type in system design. We are going to learn more about each type next. If you've ever opened an app and noticed that images appear instantly, pages load faster the second time, or some data works even without the internet, then you've already experienced client-side caching in action. Client-side caching means storing frequently used data directly on the user's device, so future requests can be served locally instead of contacting the server again. The client could be a web browser, mobile, or desktop app. Imagine an e-commerce homepage visited by millions of users daily. Without client-side caching, every user reload causes downloading of CSS, JavaScript, and image files, and also API requests. With client-side caching, all these assets and some of the API responses are already cached and exist locally. That results in faster performance, lower latency, reduced backend load, and lower costs. Whenever you open a website like YouTube, Netflix, Amazon, or Instagram, content loads quickly no matter where you are in the world. The reason is CDNs. A content delivery network, or CDN, is a globally distributed network of servers that caches and serves content from locations closer to users. Instead of requesting files from the R1 server, users fetch cached copies from nearby edge servers. The core problem that CDNs solve is that distance causes latency. Imagine your web server is located in New York. Now a user opens your website from Tokyo. If every image, CSS file, JavaScript file, and video must come from New York, this results in high latency and slow page loads. Data traveling across continents takes time. So instead of moving users closer to servers, we move content closer to users. That is the idea of a CDN. Each CDN server is called an edge or POP, which stands for point of presence. This is an example of a basic CDN architecture. User requests image, DNS routes request to nearest CDN node. If cached, then it's served immediately. If not cached, CDN fetches from origin and stores response for future requests. You may have heard the famous quote that says, "There are only two hard things in computer science: cache invalidation and naming things." That quote became popular because cache invalidation sounds simple, but in real-world systems, it can become surprisingly complex. Caching improves performance, reduces latency, lowers database load, and helps systems scale. But if cached data becomes outdated, users may see stale information. That means caching gives us speed, but invalidation gives us correctness. Cache invalidation means removing or updating cached data when the original source of truth changes. For example, let's say your database stores product prices. In the database, the price of product A is 100. So the cache stores 100 as well. Now the merchant changes the price to $80. So the database becomes 80. But the cache still says 100. Now users see the wrong price. That stale cache entry must be invalidated. So cache invalidation ensures fresh data, correct user experience, and consistency between cache and database. Message queues are one of the most important building blocks in scalable distributed systems. They help systems handle spikes in traffic, decouple services, and scale independently. A message queue is a communication mechanism where one service sends a message and another service receives and processes it later. Think of it like a mailbox. You drop a letter into the mailbox. The postal worker collects it later. The receiver reads it later. You do not need both sender and receiver active at the same time. That is exactly what asynchronous systems need. This is simply how a message queue works. A producer sends messages to the queue stores the messages, and consumers process these messages from the queue. A message is consumed once. That means after the consumer processes it, it's removed from the queue. So why do we need message queues? Imagine an e-commerce website. A customer places an order. Immediately after order placement, many tasks must happen. For example, sending a confirmation email, reducing inventory, notifying the warehouse, and more. If the web server performs all tasks synchronously, the user waits several seconds, which results in a bad user experience. Instead, the web server can save the order instantly, push the remaining tasks into a message queue, return a response to the user, and later background workers can process the tasks from the queue. This is faster and more scalable. And that's the main idea of message queues. In the previous lecture, we learned that producer components send messages to the message queue, and once a consumer processes a message, it's gone. But what if many systems need the same message? We need broadcasting. That leads us to pub/sub. Pub/sub stands for publisher, which sends messages, and subscriber, which listens for messages. The publisher does not know who receives the event. It simply publishes to a topic. Subscribers register interest in that topic. This is an example flow. The customer clicks buy now on the website or mobile app. Then the checkout service creates the order record in the database. After successful creation, it generates an event or a message and sends it to the order's topic. Now all the services that are subscribed to this topic, which are the payment, inventory, and email services, process this message. Imagine you open a coffee shop. Business is going well. People walk in, order their coffee, and you and your team handle every customer smoothly. But one morning, a bus full of tourists pulls up, and suddenly 300 people walk through your door at the same time. Your espresso machines are overwhelmed. Your staff cannot keep up. Orders start piling up. Quality drops. Some customers do not get served at all. A few regulars who just wanted their usual morning cup end up leaving because the line is too long. Now here's the thing. Your coffee shop has not changed. The space is the same. The machines are the same. The staff is the same. The problem is that the incoming demand exceeded the capacity of the system in a very short window of time. This is exactly the kind of problem that rate limiting solves in software systems. So, what is rate limiting? Rate limiting is a technique used to control how many requests a user, a client, or a system can make to a service within a given period of time. That is the core definition. If a user is allowed to make 100 API requests per minute, and they make their 101st request within that same minute, the system will reject that request. It will not process it. It will typically return an error response telling the caller to slow down and try again later. Now, why does this matter? There are 4 core reasons. The first is resource protection. Servers have finite CPU, memory, and database connections. Unlimited traffic can exhaust those resources entirely and take your service down for everyone. Rate limiting keeps demand within what your infrastructure can handle. The second is abuse prevention. Automated scripts can hammer your API thousands of times per second to scrape data, brute force passwords, or run denial of service attacks. Rate limiting raises the cost of that abuse significantly. The third is fairness. In any shared system, one heavy user can consume the majority of capacity and degrade the experience for everyone else. Rate limiting distributes resources more equitably. The fourth is cost control. A bug causing an infinite loop or a rogue client can generate enormous bills if you pay for usage. Rate limiting caps that exposure. There are several arguments used to implement rate limiting. In this lecture, we will learn about the token bucket argument. Picture a bucket. This bucket holds tokens. Every fixed interval, let's say every second, a certain number of tokens are added to the bucket. There's a maximum capacity, so once the bucket is full, new tokens are simply discarded. Now, every time a client makes a request, it must consume 1 token from the bucket. If there is a token available, the request goes through and the token is removed. If the bucket is empty, the request is rejected or queued. That is the entire argument. Let's make this concrete with numbers. Say the bucket has a capacity of 10 tokens and refills at 5 tokens per second. If a client sends 5 requests in the first second, 5 tokens are consumed, 5 remain. In the next second, 5 more tokens are added, bringing it back to 10. Now the client can send another burst of up to 10 requests instantly. This is the key insight of token bucket variable. It allows short bursts of traffic as long as the average rate stays within the refill rate. In this lecture, we are going to look at the leaky bucket algorithm, the close cousin of token bucket we learned about in the previous lecture. Let's start with the intuition. Imagine a physical bucket with a small hole at the bottom. You can pour water into the top at any rate you want, in bursts or steadily, but the water only drips out of the bottom at one fixed constant rate, regardless of how much water is inside. If you pour in water faster than it drips out, the bucket fills up. Once it is full, any additional water you pour in simply overflows and is lost. That is the leaky bucket algorithm. Requests are the water, your server is the hole at the bottom, and the overflow is rejected traffic. Now let's look at how it actually works in an implementation. When a request arrives, you check the current queue size. If the queue is not full, you add the request to the queue and return a success to the client. A separate process, often called the processor or the worker, drains the queue at a fixed rate, for example, processing one request every 10 milliseconds. If the queue is already at capacity when a new request arrives, that request is dropped immediately. The client gets a rate limit error. So the two parameters here are the queue size and the outflow rate. The outflow rate is your throughput, how many requests per second your system will actually process. The queue size determines how much burstiness you will absorb before you start dropping requests. A larger queue means you can absorb longer bursts without dropping anything, but it also means requests can sit waiting in the queue longer before being processed, which increases latency. In modern systems, applications generate massive amounts of files like images, audio files, and videos. Storing these reliably and cheaply is a major challenge. It's not efficient to store this kind of data in a typical SQL or NoSQL database, for example. This is where AWS S3 comes in. Amazon Web Services S3 stands for Simple Storage Service. It is an object storage service designed to store and retrieve unlimited amounts of data over the internet. It's highly durable, scalable, distributed, supports pay-as-you-go model, and accessible from anywhere. S3 stores objects in something called a bucket. Each bucket belongs to a specific AWS region and must be globally unique. An object is a file stored inside a bucket. Each object contains the file data, metadata, and a unique key called the object key. The key is the object's full path and name. S3 internally uses the bucket name plus the object key to uniquely identify objects. In modern distributed systems, services constantly exchange data. If services communicate directly with each other, systems become tightly coupled and difficult to scale. This is where Kafka helps. Apache Kafka is a distributed event streaming platform used for messaging between services, real-time data pipelines, event-driven systems, log aggregation, and stream processing. Without Kafka, services would communicate directly, and this makes the services tightly coupled and makes the system very difficult to scale. With Kafka, producers send messages, also known as events. Kafka stores them, and consumers read them. This makes the system more scalable and loosely coupled. Producers and consumers can scale independently. Kafka organizes the messages into categories called topics. Think of a topic like a database table for events. And topics are split into partitions. The reason for that is to introduce parallelism, make it easier to scale and increase the throughput. Every message inside a partition gets a unique number called an offset, and consumers track offsets to know what they already processed. Each Kafka server is called a broker, and each Kafka cluster contains multiple brokers. In modern systems, users expect fast search results even when datasets contain millions of records. Traditional relational databases are not optimized for advanced full-text search. This is where Elasticsearch becomes important. Elasticsearch is a distributed search and analytics engine built on top of Apache Lucene. It is commonly used for search engines, recommendation platforms, real-time dashboards, and log analytics. The problem with searching in traditional databases is that they are not efficient for full text search. For example, if you want to search for a text in a SQL database, you would need a query like this, which is slow on large datasets and has an inefficient relevance ranking. Elasticsearch solves these using inverted indexes, relevance scoring, and high scalability due to the distributed architecture. A document is the basic unit of data in Elasticsearch. Documents are stored in JSON format. Think of it as a row in a SQL database, and each collection of documents is called an index. Think of it as a table in a SQL database. Elasticsearch splits data into smaller pieces called shards. This enables horizontal scaling and improves the performance. Replicas are copies of shards. This ensures high availability, improved fault tolerance, and read throughput. A node is a single Elasticsearch server. Each node stores shards. A cluster is a group of Elasticsearch nodes working together. Elasticsearch uses an inverted index instead of scanning every document. For example, for these documents, this is how the inverted index would look like. Search becomes extremely fast because Elasticsearch directly locates matching documents. Imagine you have hundreds of servers working together in a distributed system. How do they agree on who is the leader? Store shared configuration, detecting failed nodes, and coordinate distributed tasks? This is where Apache Zookeeper comes in. Zookeeper is a distributed coordination service used to manage and coordinate distributed systems reliably. It helps systems perform tasks like configuration management, leader election, service discovery, distributed lock-in, and synchronization. Popular systems using Zookeeper include Apache Kafka, Hadoop, and HBase. Let's understand more about the problem that Zookeeper solves. In distributed systems, servers can crash, restart, lose network connectivity, or become inconsistent. Without coordination, systems become unreliable. For example, suppose 5 servers process payments. Which server is the leader? How do workers avoid processing the same job twice? How do services discover each other? Zookeeper acts like a central coordinator. A Zookeeper cluster is called an ensemble. One server becomes the leader, others become followers. The leader handles writes. Followers replicate data. Zookeeper stores data in small nodes called znodes. Its structure looks like a file system. Each znode stores small metadata, configuration, and status information. There are 3 types of znodes. Persistent znode remains even after client disconnects. They are used for app configs and permanent metadata. Ephemeral znode, which is deleted automatically when client disconnects, they are used for leader election, services registration, and health tracking. And sequential znode, Zookeeper automatically appends numbers to nodes of these types. They are useful for queues, ordering, and leader election.
Spark is a distributed computation engine built for processing massive datasets across clusters of machines. The core idea behind Spark is simple. You write a program that describes what you want to do with your data. Spark figures out how to distribute that work across many machines efficiently. So instead of thinking, how do I parallelize this? How do I coordinate threads? How do I split work across servers? Or how do I recover from machine failures? You simply define transformations on data, and Spark handles the parallelism and distributed processing of the data. Before Spark, Large-scale distributed processing was mostly done by Apache Hadoop, HDFS for storage, and MapReduce for computation. MapReduce worked, but it had major limitations. Every processing stage required reading from disk, processing, and writing back to disk. That repeated disk I/O became extremely expensive. Spark changed the game by introducing in-memory processing. That resulted in around 10 times faster even with disk-based workloads. Let's talk about Spark's architecture. At a high level, Spark consists of driver program, cluster manager, worker nodes, executors, and tasks. The driver program is the application you write, usually in Scala, Python, Java, or SQL. It's responsible for the data transformation and coordination of the executors. You can think of the driver as the brain of the Spark application. The driver communicates with a cluster manager, which is responsible for CPU and memory allocation and tasks scheduling. Spark supports third-party cluster managers or Spark's standalone cluster manager. Worker nodes are the actual machines in the cluster. These may be physical servers or EC2 instances, for example. Each worker node runs one or more executors. And finally, tasks are the smallest unit of work in Spark. If your dataset has 100 partitions, Spark may create 100 tasks. Each task processes one partition independently. This parallelism is what gives Spark its speed.
In modern system design, speed matters. Applications often become slow because databases are disk-based and require expensive reads and writes. Redis solves this problem. Redis is an open-source in-memory key-value database. It's used for caching, session management, real-time analytics, message queues, leaderboards, and distributed locking. It's extremely fast because data is stored primarily in RAM. It supports strings, lists, hashes, sets, sorted sets, streams, bitmaps, and hyperlocal. Everything in Redis is stored as pairs of keys and values. Some of the common Redis data types are strings. This is an example of storing and retrieving a string value. Usually it's used for caching, counters, and tokens. Then lists, hashes, which are mostly used to store objects, sets, and sorted sets, which are commonly used to store leaderboards. Redis is memory-based, but data can still be persisted by periodically saving snapshots to disk. Caching is a very common use case for Redis. Instead of always reading from the database, frequently requested data is served instantly. In the previous lecture, we explored Redis and saw how powerful in-memory databases can dramatically improve application performance. Now, let's look at Memcached, which is another popular in-memory caching system. Memcached is a simple distributed in-memory cache designed to reduce database load. It stores the data in RAM and has very high read and write speed. Similar to Redis, it stores the data in key and value pairs form. Since we learned about Redis already, let's understand the difference between them. Starting with the data structures, Memcached only supports strings or serialized objects, while Redis supports various advanced data structures. Memcached doesn't persist the data, while Redis persists the data via regular snapshots. Memcached is efficient for simple data caching, but generally Redis is the more popular choice. One of the most widely used relational databases is MySQL. Popular companies and platforms have used MySQL extensively because it is simple, scalable, and battle-tested. MySQL is open source, relational, ZOL-based, fast, and reliable. MySQL stores data in databases. Each database consists of tables, and each table consists of rows and columns. Each row is a record, and each column represents an attribute. MySQL is a convenient choice if the system requires data consistency, reliability, transactions, and if there are a lot of relations between the data. Some common use cases are user accounts, payments, inventory systems, order management, banking systems, and enterprise applications. In the previous lecture, we learned about MySQL, a fast, reliable relational database commonly used in web applications. Today, we'll study PostgreSQL, often called Postgres. PostgreSQL is also a relational database, but it focuses heavily on advanced SQL features, data integrity, and scalability. BaseSQL is usually for simplicity and speed, while PostgreSQL is for advanced features, correctness, and complex systems. PostgreSQL is known for strong ACID guarantees. This is critical in systems like banking systems, payment platforms, and order processing. PostgreSQL supports many index types. The default index is a B-tree index, which is best for equality lookups and range queries. Hash index, which is best for exact matches. GAN index, which is useful for JRU-MB data and full text search. And guest index, which is best for geospatial queries. So storing locations is a common use case for PostgreSQL as well. In modern system design, applications need databases that scale automatically, handle massive traffic, and remain highly available across regions. Traditional relational databases often struggle with these requirements at internet scale. This is where a NoSQL database like AWS DynamoDB becomes important. DynamoDB is a fully managed key value database built for high scalability and low latency. And it's fully managed by AWS. That means no infrastructure management required. It's horizontally scalable and distributed by default. Unlike SQL databases, DynamoDB has no joins and complex relational schemas. Instead, it focuses on scalability and speed. Instead of tables with relationships, DynamoDB uses tables, items, and attributes. DynamoDB automatically distributes data across partitions. This enables horizontal scaling, high throughput, and parallel reads and writes. The partition key determines where data is stored and which node handles requests. AWS scales automatically, so it's a convenient choice if traffic is unpredictable or rapid scaling is needed. Unlike managed NoSQL databases such as Amazon DynamoDB, Apache Cassandra is an open source distributed NoSQL database designed for systems that require high write throughput, massive scalability, and continuous availability due to its distributed architecture. Cassandra runs on multiple nodes. There is no master node or single point of failure. All nodes are equal. This is called peer-to-peer architecture. From the CAP theorem perspective, Cassandra prioritizes availability and partition tolerance, and it provides eventual consistency. It's an excellent choice if the system requires high write throughput and massive scale, and eventual consistency is accepted. Alright, let's start with installing Redis. Go to this website, then click on download, keep the default version selected, then follow the installation steps. And once the installation is completed, make sure everything is working as expected by connecting to a Redis instance via this command if you are using Docker, or if you installed Redis CLI, you can use this command. If everything worked correctly, you will see a prompt that looks like this. Now that Redis is installed and running, it's time to work with the most important and most commonly used Redis data type, which is strings. If you only learn one Redis data type, this should be it. Almost every Redis application uses strings in one way or another. Whether you're caching API responses, storing user sessions, saving configuration values, or implementing counters, strings are everywhere. Despite the name, a Redis string isn't limited to just text. It can store text, numbers, JSON, binary data, serialized objects. So think of string as Redis's general purpose value type. Every value is stored using a key. The most basic command in Redis is set. It stores a value under a key. Let's store our first value. We type set, then the key, for example name, then the value between double quotes since we are storing a string value. Now let's retrieve it. Simple. We stored the value and retrieved it. Let's add another one. then retrieve it. Every key in Redis must be unique. If you store another value using the same key, Redis replaces the old value. For example, let's set the name key to a different value. Now, if we retrieve it, we get the latest value. The previous value is gone. If we try to request a key that doesn't exist, Redis responds with that. That simply means the key wasn't found. It isn't an error. Redis is just telling us that no value exists for that key. Updating a value is just another set. For example, let's update the language key. No separate update command is needed. Simply call set again. To remove a key, we use the del command. Redis responds with a number that tells us how many keys were deleted. Sometimes you only want to know whether a key exists. Redis provides the exists command. 1 means the key exists. Now check a missing key. 0 means it doesn't exist. If you want to see all the keys stored in the database, you can use this command. This returns every key in the database. This is great for experimenting locally. However, it's important to know that you should avoid using it in production applications, because Redis has to scan every key in the database, which can become slow if you have millions of keys. One of Redis's biggest strengths is the ability to automatically remove data after a certain amount of time. For example, we can store a temporary verification code. Now let's make it expire after 60 seconds. Now the key will automatically disappear after 1 minute. Now if we want to know how much time is left before a key expires, you can use this command. That is the number of seconds remaining until this key expires. Redis provides counters that allow us to increment, decrement, and modify numbers efficiently, all without us having to retrieve the value first. These operations are also atomic, which makes them extremely useful in applications with many users accessing the same data at the same time. Let's see how this works. This is the simplest counter command. Suppose we're tracking how many people have visited our website. Initially, let's create the counter. Now increment it. Notice something nice here. Redis not only increments the value, it also returns the updated value immediately. What happens if the key doesn't exist? Let's try. Redis automatically creates the key and initializes it to 0 before incrementing it. So after running the command once, the value becomes 1. This behavior makes counters extremely convenient because you don't have to initialize them yourself. Decrement is the opposite operation. Suppose we're tracking available seats for an event. Now 1 ticket is sold. Each time a seat is sold, we simply decrement the counter. Sometimes increasing by 1 isn't enough. Maybe you're adding multiple points to a player's score. Redis provides the increase by command. Let's store a score. Now add 25 points. You can increase the value by any amount. Likewise, if you want to decrease by more than 1, use decrease by. A Redis hash is a collection of field value pairs stored under a single key. If you're coming from Python, you can think of it like a dictionary. If you're familiar with JavaScript, it's similar to an object. Instead of storing one value for a key, we can store multiple fields inside it. Visually, it looks like this. Notice that everything belongs to the single key. This keeps related data together and makes it much easier to manage. This is the command for storing values in a hash. Let's create our first user. Now our hash contains 3 fields. To retrieve a specific field, use this command. Notice that we're retrieving individual fields rather than the entire object. Sometimes we want every field in the hash. For that, we use this command. Notice the output alternates between field names and their values. This command is useful when you need the complete object. What if we only need a few fields? Instead of retrieving the entire hash, we can request only those fields. This is more efficient when you only need a subset of the data. Updating a field is just as easy. To remove a field, use this command. Now, if we retrieve it, the field no longer exists. If you need to know whether a field exists, use this command. This command lists all the keys in the hash. And this command lists all the values. This command returns the number of the fields. Earlier we learned about counters. Hashes support numeric fields as well. Suppose each user has a login count. Now increment it. This works exactly like the increment command, but on a field inside a hash. A Redis list is an ordered collection of values. Unlike hashes, where values are stored by field names, a list stores items one after another in a specific sequence. Think of it like a queue or an array that can grow from either end. Let's start by adding items to the left or beginning of the list. The number indicates the current length of the list. Now let's add another item. Sometimes we want to add items to the end instead. This is the command for it. Now let's remove items. To remove the first item, use this command. Redis returns the removed value. Similarly, this command removes the last item. Sometimes we want a specific item. For this, we use that command and pass the index of the item. Redis set is an unordered collection of unique values. There are two important characteristics here. First, the values are unique. If you try to add the same value twice, Redis simply ignores the duplicate. Second, the values are unordered. Unlike lists, Redis does not guarantee the order in which elements are stored or returned. Think of it like a bag of unique items. This is the command for adding values to a set. What happens if we try to add Alice again? 0 means nothing was added, because Alice was already in the set. This is one of the biggest advantages of sets. You never have to manually check for duplicates. Redis handles it automatically. Now let's add more items to the set. To retrieve every value in a set, use this command. Often we don't need every value, we simply want to know whether a value exists. For that, we use this command. Alice exists, now let's check someone else. John isn't in the set. This command is extremely fast, making it ideal for permission checks, authentication, and many other scenarios. To remove a value from a set, use this command. So far, we've explored several Redis data structures. Now we're going to look at something that's a little different. Unlike the other data structures, bitmaps aren't actually a separate Redis data type. A bitmap is simply a string where Redis lets us manipulate individual bits. At first, this might sound a little strange. Why would we want to work with individual bits instead of normal values? The answer is memory efficiency. When you need to track millions of simple true or false values, bitmaps can save an enormous amount of memory. Let's see what that means. Before we talk about bitmaps, let's quickly review what a bit is. A bit is the smallest unit of data in a computer. It can have only two possible values, 1 or 0. You can think of them as 0 means false and 1 means true. Because there are only two possible values, a single bit is enough to represent many yes or no situations. A bitmap is simply a sequence of these bits. Each position can represent something different. For example, it can mean if a user is online or offline. You might wonder, why would we use bitmaps? Suppose you're building an application with 10 million users. Every day you want to know whether each user logged in. One approach is to store them like that. That works. But imagine creating millions of keys every single day. That's a lot of memory. Instead, we can store one bitmap. Each user's ID becomes a bit position. Now, millions of users can be represented using only a few megabytes of memory. That's why bitmaps are so powerful. This is the command for setting a bit in a bitmap. Let's create our first bitmap. Suppose we want to record whether users logged in today. User 1 logs in. The return value is the previous value of that bit. Initially it was 0. Now user 2 logs in. Now user 4 logs in. To read a bit, use this command. Let's check whether user 3 logged in. User 3 didn't log in. Now check user 4. User 4 did log in. Simple. Imagine you're running a large website. Every day, millions of users visit your site. At the end of the day, your boss asks a simple question. Okay? How many unique visitors did we have today? Notice the word unique. If the same user visits your website 10 times, they should only be counted once. So how would we solve this? One option is to use a Redis set. Every time a user visits, we add their ID to a set. At the end of the day, we count the members. This gives us the exact number of unique visitors. So what's the problem? Memory. If you have 10 million unique visitors, Redis has to store 10 million user IDs. That can consume hundreds of megabytes of memory. For small applications, that's perfectly fine. But for very large systems, it becomes expensive. This is where hyperloglog comes in. Hyperloglog is a probabilistic data structure. That's a fancy way of saying that it doesn't give an exact answer. Instead, it gives a very accurate estimate. In exchange for that tiny amount of inaccuracy, it uses an incredibly small amount of memory. If you absolutely need an exact count, for example, counting the number of users who purchased a product, then hyperloglog is not the right choice. But if you're measuring website traffic, API usage, or other large-scale statistics, a tiny error is often completely acceptable. Let's create our first hyperloglog. This is the command for adding elements. Suppose we want to count the number of users who visit our website. That response means the hyperloglog changed. Now let's add more users. Now let's add the same user again. The structure didn't change. Hyperloglog already accounted for that user. Just like I said, duplicates don't increase the unique count. Now let's estimate the number of unique visitors. In this small example, the answer happens to be exact. But remember, hyperlog is designed for massive datasets. As the number of elements grows, the result becomes an estimate. Geospatial data simply means data associated with a geographic location. Every location on Earth can be represented using two numbers, latitude and longitude. Using these coordinates, Redis can calculate distances and find nearby locations. This is the command for storing locations. Notice the order carefully. Redis expects longitude first, then latitude. This is a common mistake for beginners. Let's create a set of restaurants. Redis stores all three locations. The nice part is that we don't have to worry about how Redis stores the data. We simply use the geospatial commands. Suppose we want to retrieve the coordinates of a restaurant. Redis returns the longitude and latitude that were stored. Now let's calculate the distance between two restaurants. By default, Redis returns the distance in meters, but we can choose another unit, for example, kilometers, miles, or feet. Suppose a customer is located near a specific location. We want to find every restaurant within 5 kilometers. Redis returns every restaurant within that radius. This is one of the most common Redis geospatial queries. Instead of checking every restaurant manually, Redis performs the search efficiently. Sometimes we don't know the coordinates. Instead, we already have a stored location. For example, we want restaurants near restaurant A. We can search around that existing number. Redis automatically uses restaurant A's coordinates as the center of the search. Pub/sub stands for publish, subscribe. Instead of applications talking directly to each other, they communicate through channels. There are two main roles. A publisher sends messages. A subscriber listens for messages. Visually, it looks like this. The publisher doesn't know who is listening. The subscribers don't know who sent the message. Redis simply delivers the message to everyone subscribed to that channel. This loose coupling makes applications easier to build and scale. Let's start by becoming a subscriber. Open one Redis CLI window and execute this command. This client is now waiting for messages. Notice something interesting. The terminal appears to stop. That's because Redis is now continuously listening for new messages on the news channel. Now open a second Redis CLI window. This will act as our publisher. Publish a message. The number tells us how many subscribers received the message. Now look back at the first terminal. The message arrived instantly. No polling. No refreshing. Redis pushed the message directly to the subscriber. Now open a third terminal and subscribe to the same channel. Now there are two subscribers. Let's publish another message. Now 2 is returned since there are two subscribers. Publish once. Deliver to everyone. That's the core idea behind pub/sub. A Redis stream is an append-only log of messages. Think of it as a timeline where new events are continuously added to the end. Unlike pub/sub, messages remain stored until you explicitly remove them. Visually, it looks like this. Every new message is appended to the end. Older messages remain available for future consumers. Let's create our first stream. Suppose we're recording customer orders. This is the command for adding messages. The asterisk tells Redis generate an ID for me. This is the message ID. Every message in a stream has a unique ID. The first part is based on the current timestamp. The second part ensures uniqueness even if multiple messages arrive during the same millisecond. Let's add another order. Redis generates another unique ID. Unlike strings or lists, stream entries contain multiple fields. Each message looks very similar to a small hash. This makes streams perfect for representing events. To read messages, we use this command. Suppose we want every message in the stream. Minus means the beginning of the stream. Plus means the end. Every message includes its ID and fields. Maybe we only want recent messages. We can specify IDs. Now Redis returns only messages after that ID. This makes it easy to process streams incrementally. If we want the newest messages first, we can do that. Redis returns the messages in reverse order. This is useful when displaying recent events. When candidates struggle in a system design interview, it is often not because they lack technical knowledge. It is because they start designing too early. A strong system designer does not immediately jump into databases, APIs, or microservices. Instead, they first clarify what the system is supposed to do. This step is called clarifying functional requirements, and this is what you should do first at the beginning of the interview. If you misunderstand the product requirements, even a technically impressive architecture can become completely irrelevant. Functional requirements describe what the system should do. These are all examples of functional requirements. As you can see, they define the core behaviors and capabilities of the product. They focus on the features of the products and the user actions. Let's see an example. Imagine the interviewer says, design YouTube. Then the functional requirements could be users can upload videos, watch videos, search for videos, and subscribe to channels. Starting the interview by clarifying the functional requirements helps you narrow the scope, show product thinking, since interviewers evaluate whether you think like an engineer solving business problems, not just someone drawing diagrams, and to build the correct architecture. In the previous lecture, we learned how to clarify functional requirements. The next step is to clarify the non-functional requirements of the system. This is one of the most important parts of a system design interview. Two systems may support the exact same features, yet one works beautifully under massive scale while the other crashes constantly. Why? Because of non-functional requirements. Functional requirements answer what should the system do, while non-functional requirements answer how well should the system do it. These include things like scalability, reliability, latency, availability, consistency, security, durability, and cost efficiency. Imagine this interview question: design YouTube. Without clarifying the non-functional requirements, you might design a small internal training portal or a global video platform serving billions. Completely different architectures. The interviewer expects you to ask questions like how many users, what is the expected traffic, is the system read heavy or write heavy, real-time requirements, what are the variability expectations. These answers shape the entire design. The core categories of non-functional requirements are scalability. This answers the question, can the system handle growth? Growth in number of users, traffic, and data. Some example questions are how many daily active users? How many queries per second? What is the read/write ratio? How much data is stored? High read traffic means more caching. Huge datasets means sharding. Global users means using CDNs. And massive writes means distributed databases. The next category is availability. This means how often is the system operational and usually expressed as uptime percentage. These are some examples. High availability usually implies replication, redundancy, load balancers, multiple data centers, health checks, and failover systems. The next category is reliability. It means does the system behave correctly over time? A reliable system avoids data loss and corruption and always produces correct results. The next category is latency and performance, which means how fast must the system respond. For example, An autocomplete system can tolerate latency, while an analytics pipeline system can. Lower latency often requires caching and pre-computation. The next category is CAPE trade-offs. You don't need deep theory immediately, but interviewers expect awareness. Then geographic distribution. You must clarify if the system is available globally or locally. This matters since global systems may need CDNs and geo-replication. After clarifying the functional and non-functional requirements, it's time to define the scale of the system and do some back of the envelope estimations. Scale matters because different systems require different architectures because they operate at different scales. Without understanding scale, you cannot properly choose databases, caching strategies, load balancing, and replication methods. The core metrics of scale in system design are daily active users, queries per second, number of reads, number of writes, total stored data, and network usage. Start with estimating the number of daily active users. Then estimate user behavior. For example, each user creates 3 posts per day and reads 100 posts per day. Then estimate the read and write traffic. For example, total writes per day equals to the number of daily active users multiplied by how many posts each user creates per day. Same for reads. For peak estimations, multiply the number by 5. If reads are much more than writes, this suggests heavy caching is needed. Then estimate storage. For example, the size of each post is 300 bytes. Since the total number of posts per day is 300 million, then the total storage per day is 90, and the yearly storage is the number multiplied by 365. This helps determine the scaling of the database, the sharding and backup strategies. Then estimate the bandwidth. For example, the response size is 5 kilobytes. Multiply this by the peak number of daily reads. Large bandwidth requirements may require CDNs or compression, for example, after estimating the scale and capacity of the system. Propose an initial architecture. Make sure that the architecture is simple, complete, and satisfies the functional requirements. The initial architecture should answer what are the core components. How do users interact with the system? Where is data stored? How do services communicate? How does the system scale at a basic level? Think of it as the version 1 design. Then later you will improve it to satisfy the non-functional requirements. The core components are the client, a load balancer, the application server, and the database. For the database choice, keep it simple. You don't need the perfect database immediately. Serial databases are reasonable when strong consistency matters, relationships are important, or transactions are critical. NoSQL databases are reasonable if the scale is massive, schema flexibility is required, or availability is prioritized. You don't need the perfect database immediately. For example, you can say, initially, I'll use PostgreSQL for simplicity and consistency. If scale becomes massive later, we can explore sharding or NoSQL alternatives. Next is explaining request flow. Now walk through the entire process. This is extremely important. Interviewers want to see whether you understand how components interact. For example, in a URL shortener system, you could explain creating a short URL, user sends long URL. Load balancer routes request. App server generates short ID. Store mapping in database. Return short URL. The next step is identifying obvious bottlenecks. Once baseline architecture exists, immediately analyze weaknesses. Ask yourself, what breaks first? What becomes slow? What cannot scale? For example, single database, which results in limited write throughput and single point of failure, or no cache, which results in repeated expensive database reads. Now we move into one of the most important skills in system design interviews, which is discussing trade-offs. This is the difference between someone who memorizes architectures and someone who actually thinks like a senior engineer. Because in real world engineering, there's no perfect design. Every decision has advantages and disadvantages, and every optimization introduces a cost somewhere else. Your job in a system design interview is not to produce the correct architecture. Your job is to justify decisions, explain compromises, and show engineering judgment. That is what interviewers are evaluating. For example, a beginner often says, we should use caching. An experienced engineer says, caching improves latency and reduces database load, but introduces consistency challenges and cache invalidation complexity. That second answer demonstrates understanding. System design interviews are fundamentally about balancing competing goals. You are constantly choosing between performance and consistency, simplicity and scalability, cost and reliability, latency and durability, availability and correctness. Interviewers want to hear what you gain, what you lose, and why the decision is acceptable. System design interviews simulate real engineering collaboration. Interviewers want to see whether you can communicate ideas clearly, break down complex problems, justify decisions, and work through uncertainty. A common mistake candidates make is designing silently. Even a good design loses value if the interviewer cannot follow the reasoning behind it. Thinking out loud reveals your problem-solving process and makes the interview feel like a collaborative design discussion rather than an exam. Strong candidates explain decisions clearly, involve the interviewer, ask clarifying questions, and discuss alternatives openly. This demonstrates communication and teamwork skills that are critical for engineering roles. Also, when you verbalize your reasoning, both you and the interviewer can identify issues sooner. So remember that interviewers are evaluating communication skills more than technical correctness. That's why you should always think out loud and avoid silence. One of the biggest differences between coding interviews and system design interviews is ambiguity. In coding interviews, the problem is usually precise, inputs are defined, constraints are clear, and expected outputs are known. But in system design interviews, the interviewer intentionally gives vague prompts like design YouTube or design Uber, for example. The goal is not just to test technical knowledge. The interviewer wants to evaluate how you think, how you communicate, how you clarify requirements, how you make trade-offs, and how you structure open-ended problems, and how you handle ambiguity. Because in real-world engineering problems are ambiguous. Sometimes interviewers intentionally stay vague, so don't panic and use structured assumptions. Try always to lead the discussion. Never ask questions like, what should I do? Instead, for example, you can say something like, I'd like to scope this system to core posting and feed generation features. Does that sound reasonable? This demonstrates leadership.
I want you to design a URL shortening service like Bitly.
Sure. I'll first clarify the requirements. For functional requirements, I assume that users can submit a long URL and receive a short URL. When users open the short URL, they should be redirected to the original URL. URLs should expire optionally. Users may want custom aliases. We should track analytics like click count, timestamp, country, and device. Is that correct?
Yes, that is fine.
I'll ignore authentication initially and focus on the core system. Now the non-functional requirements. High availability, since redirection must always work. Low latency, since redirects should happen in milliseconds. Scalability, since the system should support massive traffic. Durability, since we should never lose mappings between short and long URLs. Read-heavy optimization, since reads are much higher than writes, because redirects happen far more often than URL creation.
Good. Continue.
Let's estimate the scale. Assume 100 million new URLs per month and 10 billion redirects per month. That gives roughly 40 writes per second, which is very manageable, and 4,000 redirects per second. Peak traffic could be 10x. This is clearly a read-heavy system. Now let's estimate the storage. Each record stores a short URL key, original URL, and metadata. Assume 500 bytes per record, so 50 gigabytes per month, and 600 gigabytes per year. Very manageable with sharding.
All right, now design the high-level architecture.
I'll start with a simple architecture. Client communicates with a load balancer to distribute traffic among horizontally scaled servers that prevents single point of failure, and also, since redirects are very frequent, balancing traffic is essential. Then, stateless application servers. They are responsible for creating short URLs, validating URLs, redirecting requests, and communicating with the database. For the database, I would initially choose MySQL because mappings are simple key value style records, strong consistency is useful, and transactions are reliable. This is how the schema would look like.
Would NoSQL work?
Yes. At a very large scale, I may move to Apache Cassandra because it has extremely high write throughput, easy horizontal scaling, and distributed architecture. But initially, MySQL is simpler operationally. I'd add a cache like Redis since redirects are read heavy. In this case, also hot URLs become extremely fast. For analytics, I'd use Kafka. Since analytics should not throw redirects and asynchronous processing is better. Analytics services consume the events from Kafka and store them in an analytics database. I would go for Elasticsearch since it is optimized for fast search, aggregations, and time series analytics.
How do you generate short URLs?
Several options exist. Option 1 is hashin, hash original URL using MD5 or SHA-256. Then take the first 7 characters. The problem with this approach is that collisions are possible and duplicate URLs may produce the same output unintentionally. Needs collision handling. Option 2 is auto increment ID plus base 62. This is the preferred approach. It's deterministic, easy to generate, and unique.
Why base 62?
To create shorter URLs, URL safe characters, and efficient encoding. 62 characters provide 3.5 trillion URLs, which is very sufficient. This is the redirect request flow. User opens short URL, load balancer routes request, API checks Redis if cache hit, redirect immediately, otherwise query the database, update the cache and redirect the user, then push analytics event to Kafka.
How would you scale the database?
Eventually, a single database becomes bottlenecked. I'd shard by the hash of the short key. This will result in even traffic distribution. I'd also use primary replication. Primary handles writes and replicas handle reads. This improves read scalability and fault tolerance.
What if one URL becomes viral?
Good question. A viral URL can overload a single shard. Redis will absorb most of the reads, but we can also use CDN caching. This reduces origin traffic significantly. Now, I'll discuss some trade-offs in the choices I made for the architecture. I chose MySQL initially over Apache Cassandra for simplicity, but it doesn't scale horizontally as easily. Cassandra adds distributed complexity too early, and eventual consistency is unnecessary for the early stage. I wanted simplicity and correctness first, scale later. I used Redis. Since the system is read-heavy, this reduces database load massively, but it introduces cache invalidation complexity and possible stale data. I used Apache Kafka for click tracking. This keeps redirects fast and handles high event volume asynchronously, but it causes eventual consistency in analytics and more infrastructure complexity. Since analytics is not in the critical path, so async is worth it.
Good. I like how you consistently tied each trade-off back to system priorities instead of just listing pros and cons. You clearly optimized for simplicity first, then scaled complexity only where it was justified. That is all from me. Thanks. This was a strong solution. I want you to design a chat system like WhatsApp.
Sure. Let me clarify the requirements first. I'll start with the functional requirements. One-to-one messaging, group messaging, message delivery status, online and offline presence, push notifications, and media sharing. To keep the design focused, I'll exclude voice and video calls, stories and status, and end-to-end encryption details.
Good. What non-functional requirements matter most?
High availability, users expect messaging systems to always work. Low latency, messages should arrive within milliseconds. Scalability, the system must support hundreds of millions of users. Durability, messages cannot be lost. Ordering, messages in a chat should appear in correct order. Reliability, if the receiver is offline, messages must still be delivered later. Now, I'll estimate the scale. Let's assume 100 million daily active users and 50 messages per user per day. That gives 5 billion messages per day and around 58k messages per second on average. Peak traffic could be 5 to 10x higher. So roughly 300k messages per second at peak. For the storage, assume the average message size is 200 bytes excluding media. Since media will be stored in an object storage, so 1 terabyte per day. This scale pushes us toward distributed systems, horizontal scaling, and event-driven architecture.
All right, now propose high-level architecture.
I'll use WebSockets for real-time messaging and an event-driven backend. Chat servers maintain WebSocket connections and handle routing and authentication. They are stateless in business logic, meaning they don't store messages or user data. They only keep temporary in-memory connection info like sockets. To deliver messages to the correct server, we use Redis as a present service. It contains the mapping between the users and the servers that hold their WebSockets. This is an example mapping. Messages are sent to Kafka. This buffers high traffic spikes, ensures durability, and decouples the services. Consumers consume messages from Kafka, store in the database, check recipient presence in Redis, forward to correct chat servers by sending a message to Kafka in a specific message delivery topic, and trigger notifications if offline. For the database, I go for Cassandra, since it has extremely high write throughput, high scalability, and perfect for time-ordered messages. Media files are stored in an object store like AWS S3. This is how the schema would look like. The partition key is the conversation id, and the sort key is timestamp. This is efficient for retrieval of chat history in order.
How do you handle group messages?
The first approach is fan out on write. When a user sends a message to a group, chat server receives message, publishes event to Kafka, a consumer expands the message into individual deliveries, and each recipient gets a separate message record. This approach has very fast reads but expensive writes for large groups. The second approach is fan out on read. Only one message per group is stored, and when user opens chat, group messages are fetched. This scales well for large groups, but it requires complex client-side logic to track the read state of each message, and also expensive reads generally. At large-scale systems like WhatsApp-style apps, I would go for a hybrid model. For small groups, fan out on write, and for large groups, fan out on read. Now I'll discuss some trade-offs for the choices I made. I chose WebSockets instead of polling, since WebSockets are real-time and maintain persistent connection, while polling has high latency. I choose asynchronous communication via Kafka instead of direct communication for more decoupling and supporting massive scaling. I choose Cassandra as a database since chat systems are write-heavy and Cassandra has high write throughput. Also, Cassandra is easily scaled. Another database like MySQL has strong consistency but very difficult to scale. Eventual consistency is fine with Cassandra for this system.
Good. This is a solid production-level design. That is all from my side. Thanks. I want you to design a newsfeed system like Facebook.
Sure. First, I'll clarify the requirements. Starting with the functional requirements, users can create posts, users can follow and send friend requests to each other, users should see a personalized newsfeed, feed should display newest or ranked posts, and users can like and comment. I'll exclude stories, ads, recommendation, machine learning models, and notifications.
All right, what non-functional requirements matter here?
For the non-functional requirements, availability, since the feed must always be available because it's the main entry point of the app. Low latency, users expect feeds to load quickly. Feed should load under 200 milliseconds. Scalability, we may have hundreds of millions of users, so massive read traffic. Eventual consistency is acceptable. A new post appearing 2 seconds later is fine. Reliability, since no feed data loss is acceptable.
Now estimate the scale.
Assume 500 million daily active users. Each user opens feed 10 times per day, so 5 billion feed requests per day. That means around 58k requests per second. That's a read-heavy system. For the write requests, assume 100 million posts per day, so 1.2k posts per second. For the storage, assume the average post metadata size is 1 kilobyte. Since we have 100 million posts per day, that makes it 100 gigabytes per day, and media stored separately in object storage.
All right, now design the high-level architecture.
Sure, I'll separate the system into write path, feed generation path, and read path. Clients communicate with an API gateway as a single entry point for authentication, rate limiting, and routing. Then there are 3 services: post, users, and feed. The post service handles creating the post and storing metadata. For the database, we can use any key value store. For this application, let's use DynamoDB for its simplicity and scalability. Each new post is sent to Kafka to decouple post creation from feed generation, and the feed generation services consume the events from Kafka. Then find the followers of the post creator and fan out the post. Since feeds are read extremely frequently, I'd use Redis to cache the feed to make loading feed fast and reduce database pressure. For the feed database, I'd use Cassandra because it supports massive write throughput, it's horizontally scalable, and it's excellent for timeline style queries. These are the database schemas. For the feed database, I would partition by creator_id and cluster by created_at to optimize for feed retrieval queries. For media files, I'd use object storage like S3.
How would you generate feeds?
For feed generation, there are 2 main approaches. Fan out on write, when a user posts, push post ID into followers feed cache. This results in extremely fast reads, but expensive for celebrities who have a massive number of followers. The second approach is fan out on read. That means generate feed during read request. This results in cheap writes, but slow reads. It's better for high follower users. I'd use a hybrid approach. Fan out on write for normal users, and fan out on read for celebrities or users with a lot of followers. This is what many read systems do.
How do we rank posts?
Initially, simple scoring like the sum of the post recency, number of likes, number of comments, and relationship strength. Later, we can introduce machine learning ranking.
Good job. That is all for me. Thanks. I want you to design a video streaming platform like YouTube.
Sure. Let me first clarify the requirements. Users can upload videos, users can watch videos, users can search videos. I'll keep live streaming and video editing out of the scope.
Good. What about non-functional requirements?
For non-functional requirements, the system should have high availability because users expect videos to work 24/7. We need horizontal scalability because video traffic grows massively. Low latency, since video startup time should be very low. Durability, since uploaded videos should never be lost.
All right. Now, estimate the scale.
Let's assume 100 million daily active users, 10 million videos uploaded daily, and average video size is 500 MB. So daily storage is 5 petabytes per day. This immediately tells me we need distributed object storage like AWS S3. This system is extremely read heavy. Uploads are expensive but less frequent. For the bandwidth, assume average watch time is 20 minutes. At 5 megabytes bitrate, each user consumes roughly 750 megabits. Since bandwidth requirements become enormous, we need CDN and video chunking.
Now, propose the architecture.
Sure. I'll use an API gateway because it centralizes authentication, handles rate limiting, and routes traffic to services. The user service manages the user's profile. I separate it because user management evolves independently from video management. The video service is responsible for uploading videos and storing or retrieving video metadata. For the metadata database, I select MySQL since video and user data are very relational, and since metadata size is tiny compared to video files, MySQL is a good fit. For the video files, we can store them in an object storage like S3. Uploaded videos arrive in many formats and users have different internet speeds. When a video is uploaded and stored in S3, a video encoding task is created and sent to Kafka. The encoding service then consumes the tasks from Kafka and starts the encoding process. Multiple resolutions of the video are generated and stored again in S3. I would also go for a CDN since streaming directly from S3 would create huge latency. That speeds up global delivery since videos are cached near to users. For search, I would use Elasticsearch since performing full text search in MySQL would become inefficient at large scale. Let's examine the upload flow. User requests upload URL. Video service generates a pre-signed S3 URL. Because uploading through application servers would waste bandwidth, so it makes sense to upload to S3 directly. Upload completes. S3 emits an event. Message placed into Kafka. Encoding workers consume the message. Encoded versions are generated. Metadata updated in MySQL. Now let's examine watching a video. The user requests a video page. Metadata retrieved from MySQL. Video URLs returned. Client requests video segments. CDN serves content.
Excellent. That is a solid design for a YouTube-like video streaming platform. Well done. Let us design Uber.
Sounds good. I'll start with the functional requirements. Riders can request a ride. Drivers can go online and accept rides, match riders with nearby drivers, and track driver location in real time. For non-functional requirements, high availability, since riders must be able to request rides at any time. Low latency, since driver matching should happen within a few seconds. Scalability, the system should support millions of users. Real-time location updates. And consistency is important for ride assignment to avoid assigning multiple drivers to the same rider. Now I'll estimate the scale. Let's say 50 million daily active users, 10 million rides per day. And the average trip duration is 20 minutes, so there are 1 million concurrent active trips. Drivers send location updates every 5 seconds, and let's say there are 5 million active drivers, so there are 1 million location updates per second. This is the most demanding part of the system.
All right, now design an initial architecture.
Sure. Clients will communicate with an API gateway as a single entry point to centralize authentication, rate limiting, and routing. Then a ride service owns ride state transitions, a matching service which finds nearby drivers, a location service that stores real-time driver locations, and a notification service that sends ride requests and updates. I'll store the rides and trips metadata in a MySQL database since MySQL provides strong consistency for write records. And Redis to store active driver locations since Redis is extremely fast for geospatial queries.
Let us deep dive into driver matching.
Driver's client app sends GPS location to Kafka and the location service consumes them. Kafka allows the system to absorb spikes without overwhelming downstream services. Drivers continuously send GPS coordinates. Location service stores them in Redis using geospatial indexes. When a rider requests a ride, write service creates a ride request. Matching service queries Redis for nearby drivers. Candidate drivers are ranked by distance, driver availability, and ETA. Notification service sends requests. Then the first accepted driver wins, and the ride assignment is written.
How do you prevent multiple drivers from accepting the same ride?
Redis can perform an atomic operation. For example, let's say driver A accepts a ride. If the matching service attempts to update ride status, only one update succeeds and remaining acceptances are rejected. This prevents duplicate assignments.
How would you scale Redis?
I would shard Redis geographically so that the matching only searches within a driver's region, reducing query load and latency.
Alright, well done. That is all for me.
Thanks for watching. If you like this video, make sure to hit the like button, subscribe, and check our website for more programming courses.